If all this particle physics sounds a little bit like magic trick mumbo jumbo, we'll become a little bit more comfortable with it hopefully as we go along and use it. The point to be taken away is that you don't just invent, oh, maybe this happens. The good thing is that protons and neutrons are things that exist on Earth and upon which we can do experiments, and people did, and they could measure the energies involved. The energies involved in nuclear physics are higher, and we understand that exactly why. The energies involved in atomic physics are essentially the electric attraction between a proton and an electron at a distance of 10 to the minus 8 centimeter or 10 to the minus 10 meter, the size of an atom. The nuclear forces are approximately the right strength to hold together two protons, whose charge is the same as the charge of the electron and the proton, only with the signs different, at a distance 100,000 times closer. Remember, the force decays like 1 over r squared, so this is a factor of 10 to the 10 in the magnitude of the force. The nuclear force and the energies involved are therefore much, much larger, and this is the source of solar energy. That became clear, and as I said before, E equals mc squared is really tangential to the entire exercise. We'll deal with that when that becomes important. And it is in the early decades of the 20th century that physicists finally figured out the mechanism that allows the sun to produce such copious amounts of energy, and by extension stars, and one can imagine the sense, in fact, I think it was Leo Szilard who writes about it, of looking up at the stars and being able to say, and I understand why they shine, and that's emotional high that we want to share. So the following animation will help us follow the process by which the sun generates its energy. The process by which the sun generates its energy is called the PP chain, and we'll animate it here in a minute. The end result is that one starts with 4 protons, and through a sequence of collisions ends up with a helium nucleus. The helium nucleus has a lot of binding energy. This liberates energy. That is what lights the sun. And understanding the process, again, by doing experiments on Earth, took a long time. We're going to follow through the stages for a minute. So here we have, up here at the top, 2 protons colliding. Most of the time when protons collide, electrostatic repulsion just pushes them apart. If they're moving fast enough and aimed directly enough right at each other, then they crash into each other, and they sometimes form this unstable bound state of 2 protons, which is called helium-2. Now, helium-2, as I said, is very unstable. It decays very rapidly. We don't find helium-2 anywhere, but once in a long while, and this is the insight of Hans Bethe that really told us how the sun produces its energy, once in a long while, right here, while this ephemeral helium-2 nucleus exists, one of the protons is able to beta decay, or positive beta decay, becoming a neutron and emitting a positron and an electron neutrino. So the proton is undergoing the decay. Proton goes to neutron plus positron, conserving electric charge, and since this has negative electron number, it produces an electron neutrino. This is an important decay for us. Now, this process cannot happen with just a free proton flying around, because the neutron is more massive than the proton. That's why the decay of a neutron works, but the decay of a proton doesn't. A free proton, a hydrogen atom, is stable. But in the context of a nucleus, this helium-2 nucleus, this process is possible. The extra energy needed to create the neutron is borrowed from the binding energy of deuterium, hydrogen-2. So this converts helium-2 to hydrogen-2, because one of the protons was converted to a neutron. This is deuterium. That's a bound state. And so there's nuclear binding energy, and that provides the excess energy. Now this positron goes off, and of course, there's a sea of electrons floating around, finds an electron, annihilates, and we get some extra energy. Now we have this nucleus of deuterium flying around. We need another hydrogen nucleus, another proton, to crash into that, and that, if the conditions are just right, will form helium-3, another isotope of helium. And we need that process to happen again, the whole process with all its stages to happen again elsewhere. And then we need these 2 helium-3 nuclei to crash into each other just right. And if the collision is just right, then they merge, they form some unstable beryllium isotope or something, and the net result is that they emit 2 protons, and form a helium atom, or an alpha particle. In the process, we've had two separate weak decays. And remember, weak decays are rare, so this takes a while. An average proton in the sun has to wait 10 billion years before its turn to weakly decay. And we've liberated energy at several stages. These protons come off with kinetic energy. These positrons go off and annihilate. There's some gamma rays emitted that carry energy, and this heats the surrounding. This is how the sun produces energy. And it was the insight into this, the understanding that this process could happen, that explained to us how stars work. So this is the way the sun produces energy. This reviews the exact same process we just saw. The net result is that we had 6 protons involved, but 2 were re-emitted. So you started with 4 protons, you produced an alpha particle, 2 positrons, 2 electron neutrinos, and in the process liberated nuclear binding energy to the tune of 4.3 times 10 to the minus 12 joules. Note this is a factor of 10 to the 7th, 10 million more than was available in chemical interactions. And so chemical interactions would power the sun for 10,000 years at a power of 10 million. And you realize that if the sun converted all of its hydrogen to helium, it would be able to produce energy at its current luminosity for 100 billion years. Of course, as we'll see, the sun will never convert all of its hydrogen to helium, but this at least is consistent with that being the energy source of the sun, and indeed that's what it is. Now, why won't the sun convert all its hydrogen to helium? Well, it's not that easy to generate fusion. There are 2 crucial steps. One is, I need pairs of protons to get close enough to each other to actually experience nuclear forces. Remember, protons are positive, they don't like to come close to each other. What that means is that they need to be moving fast enough that their kinetic energy carries them close to each other despite the electric repulsion. This requires temperatures of at least 1 million, probably 10 million Kelvin. Only in the core of the sun are temperatures this high. As we will see, the sun is cooler out, so the outer envelope of the sun does not produce helium in real quantities. There's no fusion going on except in the interior of the sun where the temperatures are high. Moreover, we need these protons to crash into each other many times because on average, most of the time when they crash into each other, nothing happens. And so we need very high density, again, the density obtaining in the core of the sun. We'll talk about the density when we review our models, but only in the core of the sun, only about 10% of the sun is available for converting to helium. That reduces our estimate from 100 billion years to 10 billion years, which is roughly the lifetime of the sun. So maybe we found something. And then the other bottleneck is that the rate of fusion is restricted by the fact that 2, in fact, protons must beta decay before helium-2 breaks up, and this slows down the process, and that is what prevents the sun from essentially blowing itself to smithereens. The reaction rates inside the sun are controlled, and we'll see how it maintains a stable equilibrium.